Hello there and welcome back to the Science Sleepy Minds. Tonight, you find yourself floating. Not quite asleep, not quite awake. Just drifting through a thought experiment that starts, oddly enough, with your wristwatch. That innocent little timekeeper, ticking along beside you, may not be telling you the truth. Around you, the air feels still. But zoom out, and you're hurtling through space, riding Earth's spin at 1,000 miles per hour, and orbiting the Sun at 67,000 more. And in this subtle ballet of motion and gravity, time isn't standing still, it's stretching, shrinking, bending behind your back. The faster you move, or the closer you inch to something massive, the slower your clock runs compared to someone else's. Sound unfair? Welcome to the playground of time dilation. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop your location and local time in the comments. Let's see who's time traveling fastest tonight. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're standing in a desert, vast and silent. The stars above seem sharp enough to cut. It's the kind of night where reality feels a bit more flexible, and then, quietly, time betrays you. At first, it's just a feeling, like your body's moving a beat ahead of your thoughts. You check your watch. It says one thing, your friend's phone says another. Not by much, just a second or two. But it's off, annoying, odd. But what if it's not a glitch? Here's the deal. Time isn't absolute. That's not poetry. That's physics. In our everyday world, we treat time like it's a constant drumbeat. Same second for everyone. But more than a century ago, Albert Einstein had the audacity to say, nah, and physics hasn't recovered since. According to his theory of special relativity, the faster you move, the slower time ticks for you. And if that sounds like science fiction, buckle up, because it's already been tested, and it works. Imagine you're on a spaceship traveling close to the speed of light. You're cruising along at a leisurely 180,000 miles per second, just under light speed. Inside, you read a book, sip your freeze-dried coffee, maybe write a moody journal entry. A few days pass for you. But back on Earth? Decades, generations. Your childhood best friend has grandkids now. Your apartment is a museum, and all you did was go fast. This is time dilation, a real measurable effect where high speeds make your clock tick slower compared to everyone else's. And no, it's not just a clever theory gathering dust in a physics textbook. Time dilation shows up everywhere, from particle physics to global positioning satellites. We've built machines that race fast enough to feel it. We've flown planes that come home with pilots aged differently, by fractions of a second, but still. Even atomic clocks, those impossibly precise timekeepers, have shown that just flying them around the world causes tiny mismatches in time. We're talking billionths of a second, sure, but in physics that's practically screaming. Still, the first time people heard this idea, it sounded bonkers. In fact, back in the early 1900s, when Einstein introduced special relativity, many scientists straight up refused to believe it. A few called it mathematical mysticism, because if time itself wasn't constant, well then nothing was. Historians still argue whether Einstein fully grasped how radical his theory was at first. Some say he was just following the math. Others believe he knew it would upend reality as people understood it. Either way, the result was clear. Time isn't universal, it's personal. Quirky tidbit time. In 1971, two scientists took 4 atomic clocks, loaded them onto commercial airplanes, and flew them eastward and westward around the world. When they returned, they compared the flying clocks to ones that had stayed on the ground. And yup, the flying clocks were off, by exactly the amount predicted by relativity. That experiment was called the Haffel-Keating experiment, and it's one of those gloriously weird, I can't believe someone got funding for that moments in science. But here's where it gets juicier. This isn't just about astronauts or flying clocks. Time dilation happens to you, right now. Every time you move, whether you're biking through a park or sneezing on a roller coaster, you experience time just a smidge differently than the person next to you. It's not enough to notice. Not without extremely sensitive instruments, but it's real. And that desert? Still around you. The stars above burn quietly like they always have, but you're starting to wonder, how long have they really been shining? Because light itself is part of the story. See, the reason time dilation happens is that the speed of light is constant, always, for everyone. Which is weird, because in every other situation in life, speed depends on perspective. If you throw a ball while standing still, it travels at one speed. Throw it while running, and it moves faster. Simple. But light doesn't care how fast you're moving. It just keeps zipping along at 186,000 miles per second. That stubborn behavior forces space and time to bend to keep light's speed unchanged. It's like reality is making uncomfortable compromises to keep the universe fair. And so, clocks slow down, rulers shrink, mass increases, all because light insists on consistency. Let that sink in. You're not just a creature moving through time, you're shaping it with your motion. Every step, every heartbeat, every orbit Earth makes around the sun bends the path of time around you, just a little. So, yeah, you're time travelling, not in the flashy DeLorean-flavoured sense, but in the sneaky, physics-verified, everyday you're a little older than your cat kind of way. Even lying down in bed right now, your position in the Earth's gravity, your subtle motion through space, it all makes your clock tick slightly differently than someone else's. And we do mean slightly. You won't be waking up to find your neighbours have aged 50 years overnight. But still, isn't it strange to know you're already living in a world where time can bend? It's like gravity got jealous of space and decided to mess with time too. So as you lie there, eyes blinking slower, maybe staring at the ceiling fan doing its lazy rotations, consider this. You're not locked into one universal time. You're part of a liquid system that flows differently depending on where you stand, how fast you move, and what cosmic forces nudge against your body. It's not magic, it's physics, and yet it kind of feels like magic, doesn't it? Because the second your clock ticks different from someone else's, you've already taken your first tiny step into time travel. You're still lying there, maybe with the soft hum of your fan blending into the edges of your thoughts, when the image of a wild-haired man with a chalkboard fades into your mind. Not because you summoned him, but because he's impossible to avoid when talking about time dilation. Einstein. Yep, that guy. More specifically, Albert Einstein around 1905. He's not yet a global icon, not yet the wrinkly physics wizard you picture sticking his tongue out in black and white. No, this version is younger, working at the Swiss Patent Office, reviewing inventions by day, dreaming up new rules of reality by night, and one night, likely with messy notes scattered across a small desk, he has a thought that doesn't just bend time, it rewrites it. What if, he wondered, time doesn't tick at the same pace for everyone? What if the universe was playing favourites, stretching and squashing the seconds based on how fast you're moving? What if Newton had been sort of wrong? Now keep in mind, this wasn't completely out of nowhere. Scientists had already been poking at odd results from experiments with light, like the Michelson-Morley experiment, which tried and failed to detect Earth's motion through a supposed ether that was believed to carry light. The experiment came back with a shrug. No difference in light speed, no matter Earth's direction. Cue confusion, enter Einstein with a hot take. Maybe light doesn't need a medium to travel through. Maybe the speed of light is the same for all observers. Maybe space and time themselves have to adjust to keep that constant. Boom, special relativity is born. The core idea was simple, elegant, and absolutely headache-inducing. The laws of physics are the same in all inertial frames, which just means frames moving at constant speeds, and the speed of light in a vacuum is always the same, about 299,792 kilometers per second. No exceptions, no loopholes. So if you and your friend are both watching a beam of light, and one of you is moving fast and the other isn't, you'll both measure the light's speed as exactly the same. That sounds impossible, unless time and space themselves change to make the math work out. And so they do. Time slows down for the person in motion. Distances shrink along the direction of travel. Mass increases. The faster you go, the weirder it gets. There's an equation, don't worry, we're not getting too mathy, called the Lorentz factor, which tells you how much time slows down based on your speed. At low speeds, like cars and airplanes, the effect is almost non-existent. But at speeds approaching light, time grinds to a crawl. Let's say you're in a spaceship zipping along at 90% the speed of light. According to that math, 1 hour for you might feel like 2 hours for someone on Earth. Push the throttle closer to light speed, and the effect becomes more dramatic. At 99.9%, your clock ticks 7 times slower than an Earthbound one. And at the ultimate limit, if you could reach light speed, well, time would stop altogether for you. Of course, that's the catch. You can't actually reach light speed if you have mass. Physics draws a hard line. The closer you get, the more energy you need to keep accelerating. It's like the universe handing you a cosmic slowdown sign that gets heavier and heavier the faster you go. You can approach light speed, but never touch it. Historians still argue whether Einstein fully intended to break time this way when he wrote his 1905 paper. It was titled On the Electrodynamics of Moving Bodies, which, let's be honest, sounds more like bedtime material than a reality-shattering manifesto. Yet within its pages, time dilation and length contraction were waiting to shake physics to its core. A quirky twist here. Einstein didn't win the Nobel Prize for relativity. Nope. The committee thought it was too speculative at the time. Instead, they gave it to him in 1921 for his work on the photoelectric effect. Basically how light can knock electrons loose from metal. Not nearly as sexy as time warping, but still essential. And speaking of time warping, let's pull this back into your own sleepy reality. Look around your room again. Everything seems still. Your lamp isn't moving, your books aren't hurtling through space. But remember, you're on a planet rotating at 1,000 miles an hour, orbiting the sun at 67,000 miles per hour, and the entire solar system is swirling around the centre of the galaxy at over 500,000 miles per hour. You're always in motion, and that means your experience of time is never truly standard. Here's a fun twist. Because you're closer to the equator than someone at the poles, assuming you're not at the poles, hi if you are, you're moving slightly faster due to Earth's rotation. That means your time is ticking ever so slightly slower than someone living farther north or south. Again, the difference is minuscule, but it's real. Time, it turns out, is deeply personal, and if you're thinking, okay, but I can't feel it, fair. We don't notice these tiny shifts in daily life, but our machines do. GPS satellites, which we'll chat more about soon, rely on time so precise that ignoring relativity would throw them off by miles. Miles? From just a few nanoseconds of time dilation per day, even your phone's map app is a quiet testament to Einstein's genius. Of course, not everyone jumped aboard the relativity train right away. In the early 20th century, physicists and philosophers debated the implications of time being variable. Some thought it was a temporary fix, a stopgap until someone found a better explanation. Others embraced it wholeheartedly and started experimenting with atomic clocks and high-speed particles to test the theory. Spoiler, Einstein kept being right, and he wasn't done yet. A decade later, he dropped general relativity on the world, which brought gravity into the time-bending party. But let's not get ahead of ourselves. That's coming soon. For now, you're still lying in bed, marveling at how a quiet man in a Swiss office reshaped your understanding of time forever. Not with explosions or fanfare, but with equations, stubborn logic, and a refusal to believe that time had to tick the same for everyone. It doesn't. And that's the beautiful, weird truth of the universe. Your time is your own. You sit in your seat, peering out the window at the endless blur of stars. The engines hum softly beneath your feet. You are somehow aboard a train. Yes, a train. Barreling through the void of space at nearly the speed of light. No one told you this was possible, but here you are, nestled into a comfy seat. The vinyl armrests warm from ambient starlight. The lights flicker. A vending machine floats mid-air, clanking softly. It's stocked exclusively with freeze-dried coffee and cosmic trail mix for some reason. And across the aisle, a perfectly normal-looking clock. Now you glance down at your own wristwatch. You've been watching it tick. 1 second, 2 seconds, 3. But that other clock across the aisle is slow. Just barely. Like it's stuck in molasses. You're not imagining it. You're witnessing one of the strangest truths in physics firsthand. When you're in motion, time really does slow down. This is the thought experiment Einstein used to get people on board with his new rules of time. It's often called the train thought experiment, and tonight, you're the main character. So let's rewind a bit and break it down. Imagine you're on a high-speed train, moving at a ridiculous fraction of the speed of light. On board, everything feels normal. You're sitting comfortably, maybe sipping something warm. Inside the train, a beam of light is emitted from the floor, bounces off a mirror on the ceiling and returns. Bowing. That's your clock. Light goes up, light goes down. 1 tick. From your perspective on the train, the beam travels a simple vertical path. But what about someone standing outside the train watching through the windows? To them, the train is zipping by at insane speeds. so they see the beam of light taking a diagonal path, moving up, but also horizontally as the train moves. That means the light travels a longer distance than it did from your point of view, and since the speed of light is constant, it must be taking more time. That's right. To the outside observer, the tick takes longer, and boom, there it is. The person on the train experiences time differently than the one standing still, not metaphorically, mathematically, physically. This isn't just a thought exercise. It's been proven with high-precision atomic clocks placed on fast-moving aircraft. They tick slightly slower than identical clocks on the ground. Every time. The universe plays by Einstein's rules, not Newton's. Sorry, Sir Isaac. Historians still argue whether Einstein ever rode a train that inspired this visualization. He often used trains in his analogies, though, maybe because they were the fastest human-made transportation at the time, or maybe he just liked a good buffet car. Here's a weird side note for your sleepy brain to chew on. Some philosophers have a huge problem with this. They argue that if two people are moving relative to each other, and each sees the other's clock as running slow, then who's right? The answer is both of them. Relativity says each observer's experience of time is equally valid. There is no absolute master clock of the universe. It's all about perspective, which, let's be honest, sounds suspiciously like something your overly philosophical roommate would say right after burning the popcorn. Still, this relativity of time leads to some truly strange consequences. Imagine if you could step off that cosmic train after a journey at near-light speed. You look around, and Earth has moved on. What felt like days to you was years, or centuries for everyone else. You didn't skip time, you just experienced less of it. It's like aging with the slowest filter imaginable turned on. It's no longer just a story. This is actual time travel. Forward, not backward, but still, real. Now back to your space train, where the vending machine is still floating. One of the granola bars has given up and is tumbling slowly down the aisle. You wonder what a granola bar tastes like after 40 years of relativistic drift. Probably still dry. To add another layer of strangeness, this effect doesn't only work on humans and clocks, it applies to everything, including particles that have no clue what a train is. There's this particle called a muon, we'll talk more about it later, but here's the short version. Muons are born in the upper atmosphere when cosmic rays hit Earth. They live incredibly short lives, lasting only microseconds before decaying. In theory, they shouldn't have time to reach the ground, but they do. Why? Because from their perspective, they're moving fast and time for them slows down, giving them just enough time to survive the journey. From our perspective, their clocks are ticking slowly. From their perspective, the distance to the ground shrinks and they make it in time. Time dilation solves the puzzle both ways, which is a lovely little trick relativity does. It changes both time and space, always in a way that keeps everything making sense. As for you, still floating on that dreamy train, your own time is personal. It's not wrong, it's not broken, it's just yours. Someone else's could be ticking faster or slower, and the deeper we get into this, the less that seems to matter. A quirky side note. When astronauts return from long-duration space missions, they've actually experienced slightly less time than those of us who stayed on Earth. It's tiny, fractions of a second, but technically they've aged slower. We literally have time travelers in orbit, and they didn't need a DeLorean or a phone booth to do it. You'll start to notice a pattern as we drift deeper into this topic. Relativity isn't about wild contraptions, it's about perspective. You don't need futuristic tech to travel through time, you just need motion, enough of it, sustained, smooth, and maybe a granola bar. So here's your sleepy takeaway. Next time you're on a train, or a plane, or even just walking briskly to the fridge, you're not just moving through space, you're also bending time ever so slightly. Not enough to notice, not enough to leave your dog a century behind you, but enough for the universe to take note, and for the physicists deep in labs and lecture halls to nod and say, yep, that's time dilation, baby. You sit back in your seat, watching the stars streak silently by, and let the rhythm of the train lull you. Somewhere, another clock is ticking at a different pace, but you don't mind. You're exactly where, and when, you need to be. You're back on Earth now, or so it seems. The stars are gone, replaced by the comforting hum of suburban stillness. You're standing in your driveway, waving at your twin sibling as they prepare for liftoff. They're about to board a ship destined for a distant star cruising close to the speed of light. They wave back, grinning behind their helmet. See you in a few years, they shout as if it's nothing. But you both know it isn't nothing. They'll be gone for a decade, maybe more. and when they come back, they'll still look like they're in their 30s. You, on the other hand, might be hobbling up with a cane, muttering about how kids these days don't understand time travel. This is the twin paradox, one of the most famous and frequently misunderstood thought experiments in all of physics. A simple story with weird consequences. Two identical twins. One stays on Earth, while the other travels at relativistic speeds. When they reunite, the spacefaring twin is younger. Significantly younger. And no, it's not just a math trick, it's real, measurable, proven. The paradox is only a paradox because it feels unfair. But wait, you might ask, rubbing your temples gently, isn't motion relative? Can't the twin in the spaceship say they were stationary while Earth zipped away? Fair point. That's where things get juicy. In special relativity, all inertial non-accelerating motion is relative. But the spaceship twin has to accelerate, first to reach high speeds, then to turn around, and finally to decelerate upon return. Those shifts break the symmetry. The twin on Earth stays in the same inertial frame the whole time, while the traveller doesn't. So yes, the journey is objectively different for each twin. And when the math shakes out, the traveller has aged less. It's not science fiction, it's time dilation in action. Historically, the twin paradox has driven physicists and philosophers to rant, rave, and presumably write very stern letters to physics journals. Historians still argue whether Einstein himself fully resolved the paradox during his lifetime. Some believe it took later physicists like Max Born and Paul Langevin to clean up the mess with more precise explanations. Still, it's such an iconic example that it's shown up in everything from textbooks to cartoons. You've probably seen some version of it. Maybe it was The Simpsons, or maybe it was Interstellar. Maybe it was just your high school teacher animatedly drawing stick figures on the whiteboard while muttering about time warps and length contraction. But tonight, you don't need stick figures. Just picture yourself and your twin. Let's call them Sam. You stay behind, tending to the plants, taking up baking, doom-scrolling through social media, and watching time pass. Sam, meanwhile, zooms away at 99.9% the speed of light. From your perspective, their ship's clock ticks painfully slow. Days stretch into months, months into years. But from their point of view, they're breezing through space, watching the universe around them rush past in a blue-shifted blur. Time seems normal inside the ship. It's everything else that looks weird. And that's the beautiful symmetry of relativity. Everyone thinks they're normal. It's the other person who looks off. But again, only one of you changes direction, accelerates and returns. You wait on Earth. You age normally. They come home, barely older than when they left. Some versions of the story exaggerate for drama. Maybe you're in your 90s and Sam's still got a youthful spring in their step. But even at more modest speeds, say, astronauts on the International Space Station, the effect is measurable, tiny but real. In fact, astronaut Scott Kelly spent nearly a year aboard the ISS while his identical twin, Mark, stayed on Earth. When Scott came home, he had aged slightly less than his brother, not by much. We're talking milliseconds. But it was enough to make headlines, and it wasn't just a symbolic experiment. NASA used it to study how space travel affects the human body, mind, and genome. But tucked in with all the medical data was that eerie, unavoidable truth. Time had passed differently for the two twins. Of course, the effects only get dramatic at extreme speeds or in powerful gravitational fields, but the principle is always there, lurking, bending time just enough to matter. Here's a quirky twist you'll like. The twin paradox doesn't just play out with people, it applies to anything that moves. Particles, clocks, even your Fitbit, though it hasn't aged significantly yet. In particle accelerators, scientists routinely observe particles called mesons that live longer than expected when travelling near light speed. Their lifespan stretches because time slows down for them. So yes, even subatomic particles get the luxury of relativistic time travel. Now imagine the emotional side of this. You're the Earth twin, waiting patiently. Decades go by. You watch the seasons change, grow old, maybe raise a family. Meanwhile, your twin is living in a strange temporal bubble. When they land, it's almost as if they've jumped forward in time, skipping entire decades of your shared story. Maybe you hug, maybe you cry, maybe you hand them a smartphone and say good luck catching up, and that's where the paradox becomes more than just math. It becomes personal. Time, it turns out, is not just about clocks, it's about relationships, about shared moments, about whether you get to grow up or grow old together, Time dilation doesn't just warp seconds, it warps what those seconds mean. Of course, you don't need to get too sentimental. It's still physics, after all. But even Einstein had moments of awe at how deeply time and motion were entangled. The twin paradox is a reminder that the universe plays by rules we didn't write, and sometimes those rules are a little heartbreaking. Still, it's also a promise. A whisper from the stars that says, if you move fast enough, long enough, far enough, you just might find yourself stepping into the future. And with that, you glance back down your driveway, imagining your twins return. The same laugh, the same eyes, the same inside jokes, but a whole different age. They wave from the future, and you're still here holding the past. You're floating now, not in space this time, but in something stranger, heavier. You feel it in your ribs, your fingertips, your eyelashes, as if the very air around you has turned syrupy. Time, that dependable old companion, is dragging its feet again. But this time, it's not because you're moving fast. It's because you're falling, not physically falling. You're standing perfectly still somewhere near the lip of a deep well, or maybe the slope of a mountain that's not on Earth. The surface below you curves ever so slightly. The sky above seems distant and the stars wobble in ways they shouldn't. You're caught in the grip of something massive, something with gravity strong enough to bend not just your path, but your very reality. Welcome to the second phase of time dilation, gravitational time dilation, where special relativity played its tricks with speed. General relativity ups the ante by showing how gravity, mass itself, can stretch and squeeze time. And tonight you're right at the edge of understanding it. Let's take a quick flashback to 1915. Einstein's already blown the doors off physics with special relativity. But he's not done. He spends the next 10 years wrestling with how gravity fits into the picture. The result? General relativity, a theory that changes gravity from a force into geometry. That's right, gravity isn't a magical pull from massive objects. It's the curvature of space-time caused by mass and energy. Picture a bowling ball on a trampoline. The ball sinks in, distorting the surface. Now roll a marble nearby. It spirals inward, not because the bowling ball is pulling it, but because the marble is following the curve of the fabric. You are the marble, and Earth, the Sun, and every black hole out there, giant bowling balls. But here's the catch. That same curvature also warps time. The deeper you go into a gravity well, the slower your time runs compared to someone at a higher elevation. This isn't just a quirky side effect, it's baked into the structure of reality. So imagine this. You're living on the first floor of a very tall building. Your friend is living up on the 100th floor. You both own incredibly precise atomic clocks. You sync them, then wait. A year later, you compare clocks. Yours has ticked slower than your friend's. Why? Because you've spent that year slightly deeper in Earth's gravitational field. Gravity slowed your time just a little. We're talking billionths of a second again, but measurable, real. It's not a theory. It's an effect that GPS engineers have to correct for constantly. Because satellites orbiting the Earth experience less gravity than we do down here, their clocks run slightly faster. If we didn't adjust for that, your navigation would go totally off course, by miles each day. And yet, most people go about their lives never knowing that the Earth itself is stretching and squishing their seconds depending on altitude. Quirky side note, time passes slightly faster on the top floor of a skyscraper than on the ground floor. So technically, if you want to live longer, by a few nanoseconds, move to the penthouse. You'll also pay more in rent, so maybe don't. Let's turn up the gravity. Imagine descending towards something really massive. A neutron star, for instance, a collapsed remnant of a massive star that's packed more mass than our sun into a sphere the size of a city. The gravity there is intense. Time near its surface crawls compared to time far away. Now take it further, a black hole. As you drift closer to the event horizon, the point of no return, something eerie happens. From your perspective, everything feels normal. Your clock ticks along, your thoughts flow. But to an outside observer, your motion slows and slows until you seem to freeze at the edge. They'll never see you cross the event horizon. You'll fade into darkness, your time stretching toward infinity. This is gravitational time dilation at its most dramatic. A literal warping of time so extreme that 1 second for you could mean a billion years outside. Historians still argue whether Einstein truly believed black holes could exist, when he developed general relativity. He found the math disturbing. Many early physicists thought black holes were just a weird solution, not something that could exist in nature, but now we've photographed them, heard their gravitational echoes through space, and every time we do, we're peeking into a place where time itself starts to break down. Here's a haunting image for you. A person descending slowly toward a black hole's event horizon, waving back at a spaceship in orbit. Their hand, caught in slow motion, seems to hover forever. Their voice stretches, slows, and fades. They are falling through space, but to the observer, they're trapped in time. Meanwhile, from the falling person's perspective, it's the universe that's racing forward. Stars aging in fast forward, galaxies spinning, civilizations rising and falling, while they calmly drift into darkness. That's the paradox of gravity and time. The deeper you fall, the slower you go, yet the faster everything else seems to move. You might be thinking, cool, but I'm not planning to fall into a black hole anytime soon. That's fair. But even here on Earth, gravity leaves its fingerprints on time. There's a reason atomic clocks must account for elevation, or why physicists build timing experiments in underground labs versus mountain observatories. Even small changes in gravity cause subtle but significant differences in how time flows. A fun and oddly cute demonstration? A few years ago, scientists used atomic clocks to show that time ticks slightly faster for your head than for your feet. Because your head is farther from Earth's centre of gravity. That means every time you stand up, your brain ages faster than your toes. Sorry, feet. You're timeless. Now drift back to your stillness, the space between wake and sleep. Imagine yourself stretched gently across a field of invisible hills and valleys. These aren't physical mounds, they're space-time contours carved out by the mass of the planet beneath you. You're not just moving through time, you're sinking into it, hovering at different depths depending on your altitude, your position, even your proximity to mountains or oceans. Time doesn't pass uniformly, it pools, it drips, it drags, and the more you learn, the more it feels like the universe is a clever liar, hiding these distortions in plain sight while your clocks tick politely, pretending nothing's wrong. But now you know better, and as you close your eyes you can almost feel it. The tug of gravity not just pulling your body down, but tugging at the seconds themselves, making them heavier, slower. Maybe, just maybe, you're aging just a tiny bit more slowly than you were before you understood. You're floating again, but this time it's real, not metaphorical, not imagined, not the syrupy pull of gravity or the warped stillness of a thought experiment. You're actually in space, suit zipped, helmet secure, orbiting Earth at 17,500 miles per hour. Below you, the planet turns in slow, brilliant silence. Blues and whites swirl in a hypnotic dance, and the sun crests over the curve of the world every 90 minutes. And while you watch the world spin, your clock ticks differently from the ones on the ground. This isn't a metaphor for isolation or some deep space poetry, it's physics, cold, precise, and beautifully inconvenient. Tonight, you're drifting into the very real, very practical world of orbital time dilation. And yes, it's still time travel, just in the boring, bureaucratic, NASA-calibrated way. Let's start with this. Astronauts in low Earth orbit age more slowly than people on the ground. Not by much, mind you, just a few milliseconds over the course of a year, but measurable, always measurable. Why? Because two things are happening at once up there. First, you're moving fast. Speed causes time dilation, as we've covered. The faster you go, the slower time passes for you relative to someone stationary. At 17,500 miles per hour, that effect kicks in, enough to make a difference on precision clocks. But second, you're also farther from Earth's centre of gravity than someone on the surface. That weakens the pull of gravity around you, which actually causes time to speed up slightly. Remember, in a gravitational well, deeper equals slower time. So up here, gravity is a little lighter. That means time ticks a bit faster. Now here's the fun twist. Those two effects compete. If you're on the International Space Station, the high speed wins, so you age slower. If you're on a GPS satellite, higher up at around 12,500 miles altitude but not as fast, gravity's weakness wins, and you age faster than someone on Earth. Is your brain frowning yet? Good. Because reality doesn't always line up with intuition. Let's talk GPS for a moment. You use it all the time, on your phone, in your car, even in some smartwatches. That magical "you are here" blue dot exists thanks to dozens of satellites orbiting Earth. Each one carries an atomic clock, ticking away at unbelievable precision. But here's the kicker. If we didn't adjust those clocks for time dilation, your GPS would be wrong by up to 10 kilometers per day. That's not just annoying, that's catastrophic if you're navigating a plane, timing stock trades, or relying on emergency services. So what do engineers do? They program the satellites to run slightly slower from the start, so that once they're in orbit, affected by both motion and weaker gravity, their clocks sync perfectly with Earth time. Think about that. To get directions to the grocery store, your phone has to account for relativity. Somewhere, Einstein is grinning smugly. Let's jump to another scenario. Imagine you're an astronaut on a 6-month mission aboard the ISS. You float through modules, run experiments, take dramatic selfies with Earth in the background. Your body is adapting to microgravity, but your time is adapting too. After 6 months, you return to Earth, technically younger than you would have been if you'd stayed. Not by a lot, a few milliseconds. But still, you moved through time differently. And in theory, if you kept doing that, going up, orbiting fast, returning, you could continue to experience tiny compressions of time over and over, like shaving slivers off the clock. It's no centuries into the future kind of thing, but it adds up. Sort of like a loyalty card for time travelers. Now, a historical tangent for you. Cosmonaut Sergei Krikalev holds the record for one of the longest total time spent in space, 803 days across 6 missions. Thanks to all those orbits, he's aged about 20 milliseconds less than people who stayed on Earth. Yes, there is a man who has time travelled a full 0.02 seconds into the future, and we love him for it. Of course, he's not alone. Every astronaut has time travelled a little, is not as flashy as Hollywood would have you believe. No wormholes, no paradoxes, no vanishing kids in photos, just the quiet, relentless tick of a clock running a hair slower than yours. Let's not forget another incredible tool in this cosmic story: atomic clocks. These hyper-accurate devices have been used in airplanes, spacecraft, mountaintops, even elevators, to detect time dilation. One famous experiment involved flying 2 atomic clocks on commercial airliners, one going east, one west, while keeping a third clock stationary on Earth. When the clocks were reunited, the flying ones had diverged, exactly as predicted by relativity. That was back in the 1970s. The experiment is now known as the Haffel-Keating experiment. Quirky name, big implications. Time dilation isn't just a prediction, it's a confirmed, predictable, utterly bizarre reality. Now back to your astronaut self. You're gazing out the ISS window. Earth looks like a living map. Clouds swirl in real time. Cities glow faintly in the night. Lightning dances across oceans. You think about the people below, moving through their seconds and minutes and hours. You're up here, aging slower, watching time from a different altitude, a different frame. And somewhere down there, your twin is on the ground again. They've watched more sunsets than you, felt more minutes pass, lived ever so slightly more life in the time you've been away. Is it enough to notice? Number. But it's enough to prove, enough to remind you that time isn't a universal constant. It's local, contextual, always bending to speed and mass. Time, it seems, can be fooled, and if you play your cards right, you can make it work for you. It's humbling, isn't it? That the very fabric of time can stretch depending on where you are, how fast you're going, or even how close you are to a planet. That 2 people, born at the same moment, can live out slightly different durations, just by being in orbit or staying on the ground. So the next time someone says we've only got 24 hours in a day, you can smile and whisper, not quite. Because you know better. You're back on Earth, thankfully. No more orbiting modules or floating granola bars. You've re-entered the realm of familiar things. Streets, birds, awkward eye contact with strangers at the grocery store. But something subtle has followed you down from space. Your phone's GPS is working. And by working, we mean it's performing a series of constant relativistic calculations, just so you can figure out where the nearest taco place is. Tonight, we peel back the layers on one of the most quietly magical things in your pocket, the Global Positioning System, or GPS. And yes, it absolutely relies on time dilation to function. Without Einstein, your navigation apps would send you to the middle of a lake instead of your dentist's office. Here's what you probably don't think about while using GPS. There are over 30 satellites orbiting the Earth, at an altitude of about 12,550 miles, each one zipping around the planet twice a day, each one equipped with atomic clocks, accurate to a few nanoseconds, and those clocks are not ticking at the same rate as the clocks here on the ground. Why? Well, as you now know, time runs differently depending on motion and gravity. The GPS satellites are affected by both. They're moving fast, about 8,700 miles per hour. They're high up, so they're in a weaker gravitational field than we are. Speed slows down their time, weak gravity speeds it up. And the balance of those two effects, turns out gravity wins. The net result, the satellite clocks tick about 38 microseconds faster per day than clocks on Earth. Doesn't sound like much, right? Well, let's walk through the math. Light travels about 186 miles in 1 millisecond. So a 38 microsecond discrepancy adds up to several kilometers of error per day in GPS position readings, if you didn't correct for it. In other words, if the engineers had ignored Einstein, your map would be hilariously off. You'd try to go to work and end up in the river, or Russia, or underground. Quirky side note, when GPS was first being designed in the 1970s and 80s, some engineers were skeptical about accounting for relativity. After all, it's one thing to theorize about time dilation in labs, it's another to bake it into satellite hardware. But when test satellites were launched, the time shifts were exactly what Einstein had predicted. The math held up. Cue a flurry of quiet panic, followed by a lot of very expensive software updates. Today, relativity isn't just part of GPS, it's at the heart of it. Every nanosecond counts, literally. Let's zoom into how it actually works. Each GPS satellite continuously broadcasts a signal with its position and the exact time the message was sent. Your phone receives these signals from at least 4 satellites at any given time. By comparing how long each signal took to arrive, your phone triangulates your position, down to a few meters, or even better. But if one of those clocks is running fast, boom, you're suddenly 3 miles off course and screaming recalculating at your car dashboard. So the clocks on the satellites are pre-adjusted. They're slowed down on purpose, so that once they get into orbit and experience the effects of speed and altitude, they tick just right from our point of view on Earth. It's one of the most practical uses of relativity ever invented. Not theoretical, not abstract, just you, trying to find sushi on a Friday night, guided by a network of satellites dancing delicately through curved space-time. Beautiful. Now here's a fringy little twist for you. A few conspiracy theorists have tried to use GPS relativity corrections as proof that the Earth is flat. Their logic: if gravity warps time and GPS accounts for it, then clearly it's all rigged. Historians still argue whether irony has ever struck harder. But the reality is this: GPS is one of the most earthbound applications of Einstein's theories, and it's working perfectly, every day, for billions of people, silently. In fact, the accuracy of GPS systems has gotten so precise that we now use it for geodesy, the science of measuring Earth's shape, rotation, and gravity field. That's right, GPS helps us track the wobble of the planet itself. All of this made possible because a patent clerk in 1905 decided to think way too hard about trains and mirrors. Let's drift for a moment. Imagine watching those satellites from orbit, each one tracing a graceful path above Earth, invisible radio signals rippling outward like cosmic sonar. They're tiny time travelers, their clocks always running slightly off from ours, and yet in their weirdness they keep us anchored. You're walking through a city. Your phone chirps, maps your location, and quietly calls up 4 or 5 different Einstein-adjusted timestamps from the sky. It reconciles them in milliseconds. The blue dot appears, and off you go, blissfully unaware that time had to be bent just a little to get you to that coffee shop. There's a strange poetry in that, isn't there? Time dilation used to be an abstract mystery. Now it's behind every rideshare pickup, every food delivery, every hike you take with that one friend who refuses to follow the trail. And it's going to matter even more in the future, as we build more precise networks, launch new constellations of satellites, and inch toward quantum positioning systems. We'll be working with timescales so fine they'll make nanoseconds seem clumsy. Even our banking systems, which rely on precise transaction timestamps, are touched by this relativistic correction. Without it, syncing across global financial networks would spiral into chaos. So yes, time dilation runs the world economy, GPS, science, security. And yet, we don't feel it. It doesn't tug at our arms or flicker across our vision. It's just there, humming quietly beneath the systems we trust. So the next time you open your map app, zoom in on your location and see yourself walking in real time down the sidewalk, pause. Not because you're lost, but because you're literally watching a byproduct of relativity at work. A subtle, perfect alignment of speed, altitude, gravity, and time. You're climbing now, up a winding path that clings to the side of a mountain. The air grows thinner, crisper. Each step crunches with quiet finality. You pause to catch your breath, glance down at the lush green valley below and check your watch. Still ticking, still faithful. But what if you knew, right now, standing just a few thousand feet above sea level, that you are, technically, older than the version of you still down in the valley? No magic, no metaphor, just another strange truth. The higher you go, the faster time passes. It's not much, a few nanoseconds here or there, but it's there, measurable, real, and as your altitude increases, so does your edge in the aging race. Welcome to what might be the most grounded, everyday version of time dilation, the mountaintop minute. This is gravitational time dilation's sneaky little cousin, and it's quietly happening everywhere, at all times. It's easy to picture time slowing near black holes or aboard speeding spaceships, but it's harder to believe that your house's second floor ages faster than your basement, that your head is ever so slightly older than your feet, that hikers, pilots, and high-rise dwellers are all, in a very subtle sense, racing ahead of the rest of us. But they are. You might be thinking, come on, seconds? Nanoseconds? Does that really count? Well, to the human eye, probably not, but to atomic clocks, oh, absolutely. Let's rewind to 2010. A team of physicists at the National Institute of Standards and Technology, NIST, decided to put general relativity to the test in one of the humblest ways possible, by comparing two atomic clocks placed just 33 centimeters apart, a little over a foot. One was slightly higher than the other, and the higher one ticked faster, not dramatically, but consistently. Time was literally passing faster for the clock just 33 centimeters closer to the sky. That's how sensitive and precise our instruments have become. Einstein's theories, once dismissed as speculative nonsense by skeptics, are now confirmed down to the centimeter. And it means that yes, climbing a mountain, even walking upstairs, nudges you slightly forward in time compared to those still below. Now let's scale that up. Imagine you're spending a weekend in a mountain lodge, 8,000 feet above sea level. Meanwhile, your friend is at the beach. You both go about your day, eating snacks, taking naps, binging old sci-fi shows. But by the time you reunite, you will have aged more. Barely. We're talking billionths of a second over a weekend. But if you kept living at that altitude for years, the gap would widen, a few milliseconds over a lifetime. So technically, high-altitude dwellers, hello Denver, age faster than sea-level folks. Ski instructors, slightly ahead of surfers. Astronauts, whole other leagues of course, but it starts right here with your elevation. Here's a fun historical tidbit. The idea that gravity could affect time was radical in Einstein's day. In fact, one of the earliest confirmations of gravitational time dilation came in 1959 with the Pound-Rebka experiment. They measured the redshift of gamma rays moving through Earth's gravitational field, specifically between the bottom and top of Harvard's Jefferson Tower. Yes, Einstein was proven right in a university building with a pretty good view. Historians still argue whether the experiment's simplicity or its impact is more impressive. Either way, it showed that even the relatively weak gravity of Earth was enough to alter the flow of time, and that was just the beginning. Today we use this principle in geodetic surveying, climate monitoring, and yes, even real estate. Knowing precisely how fast time flows at different altitudes helps us understand the shape of Earth, the movement of tectonic plates, and even the rate at which glaciers are melting. All because time is sensitive, to gravity, to motion, to position. Now let's take this to the extreme. Imagine climbing Mount Everest, standing nearly 30,000 feet above sea level. The view? Spectacular. The oxygen? Scarce. But your time? Racing ahead by about 50 microseconds over the course of a week, still tiny. But imagine living there forever. If you could. Over the decades, you'd have a measurable edge on aging. People might still say you look good for your age, but now you'd know it's because time has been on your side, literally, and it's not just elevation. Airplanes too nudge time forward. Every commercial flight you've ever taken has aged you just a sliver faster than if you'd stayed grounded. A frequent flyer ages more than a couch potato. So if you're one of those people chasing Platinum Elite status, congratulations, you've also earned a few bonus microseconds of life. Quirky twist? There's a theoretical idea that if you really wanted to maximize your lifespan, you should live deep underground, move very little, and stay near a massive object. You'd experience the slowest possible time. So if anyone ever tells you lazy people don't go far, feel free to say, actually, I'm just avoiding time. Now back to your mountain. You're standing at the summit, wind tugging at your jacket, clouds coiling below. You feel taller, lighter, clearer, and maybe, just maybe, a little bit older. Not in a bad way, not in a wrinkly, I need a nap way. But in the literal, physics-approved sense. You've outrun the valley dwellers. For a moment, time ran in your favour, so you hike back down, slightly victorious. The world looks the same, but you've shifted, just a hair, into the future. And tonight, when you finally kick off your boots, sink into bed, and replay the climb in your mind, you'll carry that secret knowledge that every staircase, every elevator ride, every mountain path is a tiny silent race against time. And you've been winning more often than you thought. You're sitting still, on a park bench maybe. The kind with flaking paint and one leg slightly shorter than the others. Around you, life goes on at its usual pace. Joggers huff by, squirrels bicker in the trees, somewhere a lawnmower drones with existential apathy. And then, bam! A subatomic particle slams into Earth's atmosphere 10 miles overhead, moving at nearly the speed of light. It's not here for the scenery, it's here to die. Specifically, we're talking about a muon, a cousin of the electron about 200 times heavier, unstable, and spectacularly short-lived. If you blinked, well, too late. In its own frame of reference, a muon only lives about 2.2 microseconds before decaying into other particles. That's 0.0000022 seconds. But here's the twist. They routinely survive long enough to reach the ground. You're probably being rained on by muons right now. Thousands of them pass through you every second. And if that doesn't make you mildly uncomfortable in a fun, sciencey way, you're not listening closely enough. Let's rewind. When cosmic rays, high-energy particles from deep space, slam into our upper atmosphere, they crash into atomic nuclei and spawn a cascade of new particles, including muons. These little speed demons are born 10 to 15 kilometers above Earth's surface and immediately start racing downward at near-light speeds. With their short lifespan, they should only travel a few hundred meters before vanishing, but they don't. They travel all the way to the ground, sometimes even deeper, into rock, through concrete, and into the basements of particle physics labs where detectors quietly count their arrival. This is a perfect real-world demonstration of time dilation. From our point of view, those muons are moving incredibly fast, so fast in fact that their internal clocks run much slower. So while only a few microseconds pass for them, we see them hanging around much longer. To the muons, the world is compressed. Distances contract at high speeds, an effect called length contraction. So from their perspective, Earth's surface isn't 10 kilometers away, it's much closer. They're not defying physics, they're living in it. Time slows, space shrinks, everyone's happy. Quirky side note, muons were first discovered in cosmic rays back in the 1930s, and at the time, scientists weren't sure what to make of them. One physicist allegedly said, "Who ordered that?" A reaction that still resonates with anyone who's ever opened a shipping box and found 200 pounds of packing peanuts instead of the microscope they ordered. Historians still argue whether muons should even count as a discovery or just a cosmic prank. But today, they're one of the best natural laboratories for testing relativity. No spaceship required. Imagine for a moment that you are the muon. You're born in a violent cosmic smash-up, jolted into existence miles above Earth, and you immediately begin your descent. You're moving at 99.9% the speed of light. Around you, time slows. The world blurs. Your internal clock ticks lazily compared to the chaos outside, and in the time it takes to blink twice, you've already hit the ground. You've travelled impossibly far for something that shouldn't last long enough to travel at all. Time dilation, 1. Common sense, 0. Now let's get even weirder. Physicists at CERN's particle accelerators, like the Large Hadron Collider, routinely smash particles together at near-light speeds. producing unstable bits like muons, pions and kaons, and they watch obsessively how long those particles last. The faster they go, the longer they live. Not because they're stronger or better made or drinking cosmic smoothies, but because their time slows down. Literally. This is one of those rare cases where theory and experiment shake hands with near flawless precision. Every second of extended particle lifespan confirms Einstein's equations. Again, and again, and again. And these aren't delicate, finicky tests. They're robust, reproducible. You could launch this experiment in a university basement with a decent detector and a lot of patience, or just lie in the grass and let the muons fall through you, because they are, right now. Thousands of them, streaming through your body, your eyes, your fingertips. It's not harmful. You've evolved with them. In fact, we use them in muon tomography, a scanning method that lets scientists peer inside volcanoes, pyramids, and nuclear reactors. Wherever muons pass, they leave little clues, traces, footprints of time that shouldn't be, but are. And when they arrive on Earth's surface, detectors see what shouldn't exist. Muons that lived too long, flew too far, but they didn't cheat death. They just slowed time. Here's a fun mental image. A muon and a human holding identical stopwatches. The muon hits start and begins its life. You, on Earth, hit start too. While you tick through a full second, the muon experiences just a blink, because it's screaming downward at light-like speeds. Its stopwatch ticks slowly. Yours doesn't. The muon lives and dies in its normal 2.2 microseconds from its point of view, but we see it taking its sweet time, sort of like watching a bullet in slow motion, while the bullet thinks it's moving just fine. And the muon never knows. It doesn't feel time differently. It doesn't feel stretched or sluggish. It simply exists within its frame, unaware that the outside world thinks it's performing miracles, which, when you think about it, is a deeply human thing too. We all live inside our own frames of reference, our own ticking clocks, our own assumptions about speed and time, and sometimes, just sometimes, we're the muon, racing faster than we can understand, surviving longer than expected, quietly defying someone else's expectations. So the next time you pause under the stars, feeling the quiet of the night pressing down, remember that there are cosmic particles streaking through you at that very moment. Little bundles of mass and speed, rewriting the rules of lifespan and distance, 1 nanosecond at a time, and they don't even need a spaceship, they just need to move. You're back in motion again, not slowly climbing mountains this time or lying beneath a rain of cosmic particles. No, now you're pushing the limits, hard. You're sitting in the cockpit of a futuristic test craft, something sleek and unreasonably aerodynamic, humming with a low electric growl. There's a countdown in your ear. The world outside is a blur waiting to happen, and when the engines ignite, you're pressed into your seat like a pancake on a rocket-powered waffle iron. Time, at first, seems normal, but as your speed increases, something strange happens. Your clock is falling behind. Tonight, you're gunning it toward the edge of relativity, exploring just how far we've come and how far we might go in testing the speed-time barrier. This is where speed becomes the ultimate distorting lens, and time, that steady, sensible friend, begins to misbehave. Let's start slow. Well, relatively slow. The fastest humans have ever travelled, so far, was during the Apollo 10 mission. In May 1969, the spacecraft hit speeds of 24,791 miles per hour, or just over 11 kilometers per second. That's fast enough to get from New York to London in under 20 minutes, also fast enough to turn your stomach into soup. But in the grand cosmic scheme of things, that's a stroll through the park, because time dilation doesn't really strut its stuff until you're cruising at a significant fraction of the speed of light, 186,282 miles per second. To get any truly juicy time bending, you need to be travelling at, say, 90% of light speed. At that velocity, your clock ticks at just 44% the rate of someone at rest. So a year for you feels like 2.27 years back home. Push that to 99%, and you're experiencing 7 times less time than Earthlings. Go 99.9999%. Now we're talking hours versus centuries. Speed becomes a time machine. This isn't hypothetical. Particle physicists do this every day. In accelerators like the Large Hadron Collider, protons are flung around a 17-mile underground ring, at 99.9999991% the speed of light. At that velocity, their internal clocks slow down so dramatically that they can survive far longer than they otherwise should. Remember our friend the muon? At rest it decays in microseconds, but spin it around at high speed and suddenly it's living. Time dilation is so extreme in these cases that particles destined to vanish in a blink are still hanging around after the blink's done blinking. Quirky tidbit: the lifetime of particles in these accelerators stretches by thousands or even millions of times due to speed. It's like turning seconds into years, all without violating any physical laws. And here's where it gets extra sci-fi-y. What if you could do the same? You, strapped into a relativistic spacecraft heading toward the nearest star system, say Proxima Centauri, 4.24 light-years away. At near-light speeds, you could get there in what feels like a few months. Meanwhile, back on Earth, over 4 years pass, and when you return home, everyone's older. You're still fresh-faced, relatively speaking. You've leapt forward through time without needing a wormhole, a flux capacitor, or an ancient prophecy. Just velocity. Now, some real-world flavour. Scientists are working on hypothetical propulsion systems that could one day allow us to achieve a fraction of these speeds. Concepts like light sails, which use the pressure of photons from lasers or sunlight, are being developed by projects like Breakthrough Starshot. The idea? Launch a gram-scale probe to another star system at 20% the speed of light. At that velocity, relativistic effects absolutely kick in. Even communication would get weird. If the probe sends signals back home, they'll arrive time-stretched, distorted by the high-speed journey. We'll have to correct for time dilation just to hear what the probe's tiny robot brain is trying to say. And speaking of corrections, let's not forget the less glamorous, but no less fascinating, tests of speed-induced time dilation here on Earth. In the early 1970s, scientists flew extremely accurate atomic clocks around the world on commercial jets. They found that the airborne clocks had experienced less time than the ones on the ground. The differences were minuscule, fractions of microseconds, but they were exactly what Einstein had predicted decades earlier. Historians still argue whether those results were dramatic enough to convert skeptics, but they were enough to rewrite flight manuals and satellite protocols. Today, physicists use storage rings to hold particles at constant high speeds and study their behavior over time. These rings don't just bend the particles' paths, they bend time for them, carefully, predictably, over and over again. But back to you, still in your seat, still accelerating. There's a thought experiment known as the relativistic rocket. Imagine a ship that can accelerate constantly at 1g, Earth gravity. You'd feel just like you do walking around on the surface, except you're gaining speed. Fast. After a year of constant 1g acceleration, you'd be moving close to the speed of light. And from your frame of reference, you could reach the centre of the galaxy in a matter of years. To observers back home, it would have taken tens of thousands of years. This is known as the Andromeda paradox. It's not about physical impossibilities, but perspective. Two people walking past each other on a street, moving at just slightly different speeds, can technically experience the now of distant galaxies at different times. Let that melt your brain for a second. You're walking one direction, someone else passes going the other. From your perspective, a decision made in a galaxy 2.5 million light-years away might already have happened. To the other person, it's still pending, all because of motion. This is where the line between physics and philosophy gets blurry and delightful. Because time dilation isn't just a consequence of speed, it's a fundamental rethinking of what time is. Not universal, not objective, but deeply personal. And if you push hard enough, if you accelerate fast enough, you can watch centuries crumble into minutes, civilizations into lunch breaks. But here's the fine print. You can't go faster than light. No matter how much fuel you burn, how many rockets you strap to your dreams, light speed is the ultimate cosmic speed limit. It's not just a suggestion, it's a wall of math and logic. As you approach it, your mass increases, your energy requirements skyrocket, and your time stretches toward infinity. You can approach the speed of light, but you'll never cross it. So yes, you can go fast enough to slow time, you can ride that edge, skim forward through decades in the blink of your own eye, but the past? That stays behind, for now. Still, you're not discouraged, you're exhilarated, because every increase in speed is a glimpse into a stranger universe, one where time melts, contracts, and unravels. And even if you can't outrun light, you can outrun your own aging. at least for a while. So go ahead, floor it, time's watching. You're standing in front of a glowing sign that reads, Speed Limit, 299,792,458 meters per second. Below it, in smaller letters, violators will not be fined. They will simply cease to exist as matter. This is not a road sign. This is the cosmic speed limit, set not by any government, but by the very fabric of space and time. Welcome to the hard wall of physics, the speed of light. It's fast, really fast, but it's also uncrossable, at least for anything with mass. And tonight, you're here to test that boundary, inching toward it with philosophical curiosity and just a hint of reckless ambition. Let's start with the basics. The speed of light in a vacuum is roughly 186,282 miles per second. Or, if you prefer more intimidating numbers, that's 670 million miles per hour. And unlike speed limits on Earth, this one doesn't have loopholes. Try to exceed it, and the universe doesn't just say no, it says that's not a thing. Not with mass, not with momentum, not even with your most inspirational playlist blaring in the background. But why? Well, here's the thing. As you accelerate a mass to higher and higher speeds, its relativistic mass increases. That means it takes more energy to keep accelerating, and as you get closer to light speed, that energy requirement grows exponentially. Approach 99% of light speed, and you're burning through fuel like it's gossip in a small town. Approach 99.999%, and you'd need the energy of entire cities, maybe even planets, just to push yourself a tiny bit faster. Try to hit the actual speed of light, and the required energy becomes infinite. You'd need an infinite amount of fuel. From a practical standpoint, that's inconvenient. From a physical standpoint, that's impossible. So light, the fastest thing we know, remains untouchable. Photons travel at light speed because they have no mass. They're not weighed down by inertia or self-esteem. They simply are. They move at light speed by default, without acceleration, without resistance, without asking permission. And you have mass. No offense. It's the single most inconvenient trait when it comes to time travel. Because light speed isn't just about movement, it's also about time. The closer you get to light speed, the slower your time runs compared to the rest of the universe. And if you could somehow reach light speed, your personal time would freeze. Yes, freeze. A photon, traveling from a distant star for millions of years, doesn't experience any time at all. From its own perspective, it was emitted and absorbed in the same moment. No journey, no passage of time, just snap here to there. It's one of the weirdest ideas in all of physics, and that's saying something. Historians still argue whether Einstein fully appreciated the philosophical horror of what he'd discovered. The idea that light doesn't just move fast, it lives outside of time entirely. But let's not get too dreamy. Let's talk about tachyons. These are hypothetical particles that always move faster than light. The catch? They've never been detected. They're purely theoretical, but they make for fascinating conversation over decaf at physics conferences. Tachyons, if they exist, would lose energy as they gain speed. Yes, backward, upside down, Twilight Zone rules. And some equations suggest they could be used to send messages backward in time, which is obviously where things get spicy. Because once you allow backward time communication, you open the door to paradoxes, grandfathers in trouble, universes collapsing in on themselves, the usual. Physicists have debated this fiercely. Some say tachyons must not exist because they break causality. Others shrug and say, well, the math works. So, maybe. But no one has ever found one, not even a hint. Still, that hasn't stopped science fiction writers from falling in love with the idea. Tachyons have shown up in everything from Star Trek to Watchmen, usually doing something ominous and quantum sounding. But if you want to stay grounded, ironically, let's talk about why the speed of light matters so much to relativity. Einstein's equations rely on it being constant, not just fast, but the same for everyone, no matter how fast they're moving. That's what makes all this time dilation and length contraction stuff even possible. In other words, light doesn't adjust its speed to match your frame of reference. Instead, space and time adjust themselves to make the math work out. Reality bends to preserve light's speed. It's a stubborn, rule-abiding, divinely consistent thing, and it also sets the speed limit for information. Nothing, not a signal, not a thought, not a poorly spelled text, can travel faster than light. which means the universe has a built-in delay, a cosmic buffering symbol, if you will. When you look at the stars, you're not seeing them now, you're seeing them then. Light from the sun takes over 8 minutes to reach you. From Proxima Centauri, over 4 years. From the Andromeda Galaxy, more than 2 million years. You're always living in the past. Observationally, anyway. And because light is the fastest way to transmit information, the universe literally prevents you from seeing anything in real time, unless it's right in front of your face. So if aliens waved at us from a distant galaxy, we'd get the message long after their civilization might be gone. And if we waved back, they'd have to wait eons to ignore us. But here's a fun speculative twist. There are ideas floating around in theoretical physics, emphasis on theoretical, about warp drives. Not warp drives like in Star Trek, where everyone's hair stays perfectly styled during faster-than-light travel. We're talking about something like the Alcubierre drive. This idea suggests a spacecraft could compress space in front of it and expand space behind it, creating a bubble that moves faster than light relative to the outside universe, but not violating relativity since the ship inside the bubble isn't technically moving. Tricksy, but promising. Of course, this would require negative energy or exotic matter, neither of which we've figured out how to produce or maintain. Also, the energy requirements might be larger than the mass of the observable universe, so not great for weekend trips. Still, it shows that even with hard limits, physicists are always poking at the edges, looking for loopholes, testing the code of reality. But until then, you and I are bound to sublight speeds. Not a bad deal, really. After all, even at 90% of light speed, you'd arrive in the future. Older than your friends, weirder than your memories, a little displaced, but very stylish. So the next time someone complains about the speed of their Wi-Fi, you can smile gently and say, well, nothing goes faster than light anyway. And if they roll their eyes, let it go. Their sense of time just isn't relativistic yet. You're asleep, or maybe you're not. It's hard to tell. You're somewhere between consciousness and dreams, and in that fuzzy space you wake up on a starship, quiet, sleek, with soft blue lights pulsing like a heartbeat around you. No engines roar, no footsteps echo, just silence, humming with the faint promise of movement. You're in a cryo-sleep pod, a little cold, a little stiff, definitely confused. You look out the port window and see nothing but stars, stretched, smeared and distorted by the ship's incredible speed. You've been asleep for a very long time, but not as long as Earth has waited for you. Tonight, you're living the most popular fantasy born from time dilation, spaceship sleep and cryo dreams, the elegant cheat code for fast-forwarding through time. And it's not all fiction. In a universe where the speed of light refuses to budge, and where even our fastest spacecraft crawl compared to cosmic distances, sleeping through time is not just a trope, it's a survival strategy. Let's start with the basics. We've already covered how travelling close to the speed of light slows time for you, the traveller. At a high enough velocity, what feels like a few months on board could be decades back on Earth. This is the classic Einstein-style time dilation. But what if, instead of moving quickly, you simply slowed yourself? Enter cryosleep, a concept found everywhere from Interstellar to Alien to 2001, a space odyssey. The idea is deliciously simple. Put humans into a state of suspended animation to survive long journeys through space. Conserve oxygen, water, food, patience. Wake up when you get there, preferably just in time to save the day or find something terrifying. In real science, we call this therapeutic hypothermia or metabolic suppression. We've already used it here on Earth, for humans. Doctors cool trauma patients or cardiac arrest survivors to lower their metabolism and protect brain function. Some surgeries rely on deep cooling to pause parts of the body mid-operation. So, yeah, we've kind of cryo-napped already, and NASA? They're paying attention. They've studied how lowering a crew's metabolic rate could reduce the burden on life support systems during long space missions. Imagine a Mars trip where astronauts sleep most of the way, bundled in a controlled stasis monitored by AI, and woken up just before landing. It's not science fiction, it's being tested. But let's return to time dilation, the real reason why your shipboard nap is more than just restful. Even if cryosleep doesn't directly change how time flows, pairing it with high-speed travel gives you a clever trick. You skip time both mentally and physically. Here's how. Imagine you're travelling to a planet 100 light-years away at 99.9999% the speed of light. Thanks to time dilation, the journey might only take a few months from your perspective. But back on Earth, 100 years have passed. Cryosleep isn't even necessary for that kind of leap. It just makes the trip easier on your sanity. You go to sleep in one era, wake up in another. It's not magic, it's math. And that's what makes it so fascinating. And in fact, some scientists have joked, seriously, that the first humans to reach distant stars might not be explorers, but corpuscles. People frozen for the journey, thawed after centuries, arriving in a future they didn't prepare for. Quirky fact, there are already companies offering cryonic preservation of human bodies today. You die, they freeze you, and store your body in liquid nitrogen, on the off chance that future medicine can bring you back. Do they work? No one knows. The scientific community is deeply skeptical. Cryonics is often described as hopeful preservation, rather than actual stasis. Historians still argue whether this is optimism, vanity, or a very expensive freezer hobby. But here's where it gets fun. Whether or not you're in suspended animation, your relativistic ship is still bending time around you. From the Earth's point of view, you're gone for centuries. From your point of view, it was just a short nap, a few dreams, maybe a cryo coffee afterward. This leads to an eerie consequence. When you return, everything you knew is likely gone. Friends, family, cultures, political memes, all ancient history. In that sense, time dilation doesn't just move you through time, it disconnects you from it. You're not just arriving in the future, you're arriving out of context. And that's the emotional edge of this concept. It's not just physics, it's loneliness. Adventure laced with alienation. Imagine waking up to a world that no longer knows your name. Imagine being the only person alive who remembers the 21st century. You step out of your sleek relativistic ship, and the buildings are taller, the language has evolved, and the Taco Bell logo has changed again. You're not just a traveller, you're a relic, the ultimate immigrant. Of course, that hasn't stopped science fiction from romanticising the idea that you could sleep through centuries, then step out onto some distant alien world, fully rested, perfectly preserved, and just a little grumpy from space dreams. But even without cryosleep, velocity alone can be your slumber. You don't need to be frozen, you just need to be moving fast enough to remember. Time dilation only cares about speed and gravity. So even if you were wide awake, journaling your relativistic voyage with dramatic flair, you'd still be sleeping through time compared to Earth. And that's what makes this whole thing so powerful. You don't need a wormhole, you don't need magic, you just need motion. So here you are, curled in your cryopod, hair slightly messed up, dreams tangled with constellations. You've been asleep for what feels like hours, but outside, decades have passed, maybe centuries. You're a time traveller, and you haven't even opened your eyes yet. You're drifting again, but this time the motion is downward, slow, silent, relentless. You're falling toward a shadow so deep, even light itself doesn't come back out. Below you space warps, stars bend, time stretches. You're approaching the ultimate time trap, a black hole, and not just any black hole, a supermassive one. Maybe the one lurking quietly at the heart of our galaxy, Sagittarius A star, with the mass of 4 million suns packed into a sphere smaller than your solar system. Tonight you're crossing the threshold of eternity, and time, your old reliable, has officially stopped returning your calls. Here's the setup. Black holes aren't just collapsed stars. They're regions of space-time where gravity has gone full diva, bending everything around them, including time, into new and terrifying shapes. The closer you get to a black hole, the slower time flows for you, relative to an observer far away. But near the edge, the event horizon, this effect becomes absurd. Let's say you're in a spaceship descending toward the event horizon. From your point of view, everything seems normal. Your heartbeat, your thoughts, the steady stream of space chill music in your helmet. But to someone watching from a safe distance, say your ex on a space station, they'd see your ship slow down, gradually, painfully, until you seem frozen right at the edge. To them, you never actually cross the event horizon. You just fade. Your image gets dimmer, redder, stretched out into oblivion until you disappear completely. That's gravitational time dilation taken to the extreme. Time near a black hole slows down so much that, from your perspective, the universe outside starts to fast forward. Seconds for you become years out there, then decades, then millennia. You could, in theory, orbit close to a black hole, pull back out, and discover that thousands of years have passed elsewhere while you experienced mere hours. Not a metaphor, not a sci-fi twist. Real physics. In fact, this isn't just theory, it's something we've already measured. In 2015, the Event Horizon Telescope began capturing real data on black holes, including the now iconic photo of the glowing ring around M87's supermassive black hole. That glowing ring? It's not just hot gas, it's light caught in time, circling the drain for so long it's practically immortal. And here's the spookiest part. Some photons orbit a black hole forever, caught in a gravitational loop, like anxious introverts pacing at the edge of the abyss. Let's talk thought experiments. Picture yourself orbiting just outside the event horizon, in a fast, stable loop. Possible in theory if you're careful and have ridiculous tech. You glance at your ship's clock, 2 hours pass, then you climb out of orbit, return home, and find out 600 years have passed. Everyone you knew is gone. Your language is outdated. TikTok is somehow embedded in human thought. And all you did was hang out by the edge of forever. This idea was beautifully explored in Interstellar, where the characters visit a planet orbiting near a supermassive black hole. Due to its extreme gravity, every hour on the surface equals 7 Earth years. That's not movie magic, that's relativity. Yes, physicists nitpick the details. No, the tidal forces from the black hole probably wouldn't be survivable, but the time math? Solid. Historians still argue whether black holes were taken seriously before the late 20th century. Einstein himself found them unsettling, and for decades many physicists believed they were just mathematical oddities. But now, we have proof. Observations, photos, gravitational waves from colliding black holes, captured by detectors like LIGO. They're not rare, they're not hypothetical, they're everywhere, and each one is a time well, a funnel in the universe where seconds spiral downward and never climb back out. Let's get even darker. Imagine falling in, past the event horizon, no going back. From your perspective, you cross the threshold in a flash. There's no freeze frame, no spooky pause. You just fall. Space itself stretches. Time becomes tangled. All directions point inward, like an Escher painting wearing a lab coat. You approach the singularity, a point of infinite density where our physics breaks, where time itself may come to an end. We don't know what happens there, not because we haven't guessed, but because our math literally stops working. The laws of general relativity can't handle it, and quantum mechanics, which rules the tiny, doesn't know what to do with gravity this intense. Some scientists think the singularity might not even be a place. It could be a boundary of logic, a point where time and space stop having meaning. Others think new physics, quantum gravity, string theory, who knows, might reveal the truth. But until then, the singularity remains the universe's ultimate spoiler-free mystery. Let's climb back out before things get too weird, because just being near a black hole is enough to make you a time traveller. This leads to some fascinating possibilities. You could, in theory, park near a black hole and wait. Let the rest of the universe rush ahead while you sip coffee at a glacial pace. You could emerge later, centuries later, without aging much. Not as dramatic as faster than light travel, but real, achievable. Time travel, courtesy of mass and patience. A quirky tidbit. In the 1970s, physicist Kip Thorne and colleagues explored the possibility of using spinning black holes to create wormholes or time machines. The math gets dicey. You'd need negative energy, perfect conditions, and probably some extremely cooperative black holes. But it's not impossible, at least not yet, and that's what keeps drawing us back to these monsters at the edge of physics. They're not just destructive, they're revelatory. They show us how fragile our ideas of time really are, how local, how dependent on where you are, how fast you're going, and what's pulling at you. Because near a black hole, time isn't just slow, it's a whisper, a stretch, a story that never finishes its sentence. And tonight, as you pull back from the edge, climbing away from the abyss, you carry with you the haunting truth that in the deepest parts of space, time becomes less of a river and more of a still pond. Dark, silent, infinite. You're not falling anymore. This time you're slipping, not through gravity, not through velocity, but through something stranger. You're in a corridor. It's dark, a little dusty, maybe cobwebbed. The air hums with low, impossible frequencies, and at the end of the hall, a doorway. Except it's not a doorway, it's a wormhole, and tonight you're about to peek through it. No, this isn't science fiction. Not entirely. It's speculative physics. Real equations, real possibilities, real debates, and a tantalizing hint that time might not just be something we move through, but something we could skip around in. Let's start with what a wormhole actually is. A wormhole, also called an Einstein-Rosen bridge, is a theoretical tunnel through space-time. Two distant regions of the universe, or even two different times, connected by a shortcut. Like folding a piece of paper and punching a pencil through it. Want to get to Alpha Centauri? Instead of travelling the long, slow path through normal space, you dive into a wormhole and pop out the other side almost instantly. Except they're not that simple, of course. The concept was born from Einstein's own field equations. In 1935, he and physicist Nathan Rosen found a solution to general relativity that hinted at such a bridge. At the time, they didn't think much of it. It looked unstable, unusable, like theoretical wallpaper. Historians still argue whether Einstein ever believed wormholes could actually exist. He seemed skeptical, but other physicists later on were not. Enter Kip Thorne, yes, the same guy who consulted on Interstellar, who brought wormholes back into the limelight in the 1980s. He and his colleagues proposed that, with the right kind of matter, a traversable wormhole might be possible. What kind of matter? Oh, just something with negative energy density, exotic matter, a substance that would repel rather than attract. Something that violates the so-called energy conditions in physics. Totally chill, just invent a form of matter that doesn't exist yet. No big deal. But here's the twist. Quantum field theory suggests negative energy might be possible. Under certain conditions, the Casimir effect, a phenomenon observed between two closely spaced metal plates in a vacuum, creates a region of negative energy. Tiny, experimental, but it opens the door. The question becomes, if we had enough negative energy, could we stabilize a wormhole? And more importantly, could we use it to travel through time? Here's how the theoretical time loop works. 1. You create a wormhole, a bridge between 2 points in space. 2. You take one end of the wormhole and move it at relativistic speed. Time dilation kicks in. That end ages more slowly. 3. Bring it back to the original location. Now from the outside, the two ends of the wormhole exist at different times. Go through the newer end, you come out in the past. Go through the older end, you leap into the future. Congratulations, you've built a time machine. Except paradoxes. So many paradoxes. You've heard them before. What if you go back and stop yourself from building the wormhole? What if you bump into your younger self and hand over lottery numbers? What if you sneeze wrong and butterfly affect the planet into becoming a giant goose-themed dictatorship? Physics doesn't like paradoxes, so some theories, like Novikov's self-consistency principle, propose that any time travel must be consistent with history. No matter what you do in the past, events will unfold in a way that keeps the timeline intact. You can travel, but you can't change. Others suggest a branching universe model. Each timeline you affect spins off into its own reality. You didn't rewrite the past, you created a new one. Multiverse enthusiasts rejoice, but there's still the big question, can we ever actually make a wormhole? As of now, no, not even close. We don't have exotic matter, we can't shape space-time like a playground, and we don't fully understand how to prevent a wormhole from collapsing instantly under its own gravity. Most models say it would close the moment you tried to send something through, like slamming a door as you step inside. But physicists haven't ruled them out. In fact, recent papers in quantum gravity and string theory suggest that under very specific conditions, possibly involving entanglement, extra dimensions, or even quantum foam, wormholes might be stable, or at least plausible. Quirky side note, there's a hypothesis called ER equals EPR, proposed by Leonard Susskind and Juan Maldacena. It suggests that entangled particles, tiny quantum-linked pairs, might be connected by microscopic wormholes. If true, that would mean wormholes aren't rare cosmic anomalies. They're everywhere, all around us. Tiny, tangled, and totally unnoticeable, like the Wi-Fi of the universe. But until we find one big enough to crawl through, wormholes remain speculative. Still, they matter. Not because we can build them tomorrow, but because they represent something larger. A reminder that space-time is not flat. It's bendable, twistable, touchable by gravity and motion and energy. Time isn't a straight arrow, it's a fabric. and that fabric might have shortcuts, folds, or loops. And if it does, then time travel, real, measurable, spaceship-level time travel, might be just an engineering problem, a very, very difficult one. So here you are, standing at the mouth of a wormhole that doesn't quite exist yet. You peer inside and see another place, another time, maybe another version of you waving back or watching reruns of a show you haven't seen yet. And for just a moment, you feel the pull, not of gravity, but of possibility. What if? What if time isn't just something we endure, but something we can navigate? The door flickers, the corridor stretches. You don't step through, not yet, but you smile. Because now you know, it's not just science fiction, it's science, with an asterisk. You're standing in a clean white room, surrounded by humming machines and blinking lights. No wormholes, no black holes, no starships, just time and a few very competitive scientists. Tonight you've wandered into the strange and obsessively precise world of atomic clocks, devices so accurate they can detect time dilation from just walking up a flight of stairs. You're now in the domain of chronometry, where physicists duel over nanoseconds, mount experiments on mountaintops, and fine-tune time so precisely that the universe itself would struggle to keep up. This is not an exaggeration. Let's start with the basics. What is an atomic clock? You might picture a grandfather clock with a little uranium pendulum. But no, these are not ticking bombs on display. Atomic clocks measure time by tracking the natural oscillations of atoms, specifically the frequency at which electrons jump between energy levels. The most famous atomic clock model? The cesium standard. In fact, 1 second, our definition of it, is now based on the vibration of cesium atoms, 9,192,631,770 cycles of radiation from the transition between two energy states of a cesium-133 atom equals 1 second. That's not poetic. That's how we actually define time now, on an atomic level. And it works beautifully. These clocks are so consistent they'd only gain or lose about 1 second every 100 million years. Which is why scientists started using them to prove Einstein right. Again, let's revisit the Hafele-Keating experiment for a moment. Those glorious days in the 1970s when physicists said, let's fly some atomic clocks around the world and see what happens. They put cesium beam clocks on commercial airliners, flew them eastward and westward, then compared their ticks to reference clocks that stayed behind. And guess what? Time had diverged, just as relativity predicted. The eastward flying clock going with Earth's rotation moved faster and thus aged less. The westward clock resisting Earth's spin moved slower and aged more. Both effects, though tiny, matched Einstein's equations with eerie precision. It wasn't just theory anymore. It was verified time travel, courtesy of Boeing and some very expensive suitcases. Quirky side note. The experiment almost didn't happen because of airline logistics. Coordinating flights and ensuring power to the clocks was a nightmare. But the data they brought back changed everything. Since then, the atomic clock game has gone wild. Scientists have taken clocks up in hot air balloons, into satellites, onto mountaintops, even across rooms just a few feet apart. And every time the results are consistent. Clocks at higher altitudes tick faster. Clocks in motion tick slower. Time bends to gravity and speed. Most recently, optical lattice clocks using strontium atoms instead of cesium have shattered records of precision. These beauties tick so accurately they'd lose only 1 second in 15 billion years. 15 billion. To test them, scientists placed 2 of these clocks just a centimetre apart, vertically, and still detected a time difference. That's how sensitive time has become. If your watch were that accurate, it would correct itself before you even noticed it was wrong. And this isn't just for bragging rights. These clocks are helping redefine our understanding of the shape of Earth, detecting subtle shifts in the planet's gravitational field, even measuring the potential gravitational waves from space. Because when you can detect time at this scale, you're not just keeping track of seconds, you're mapping space-time itself. Let's go up a mountain. You hike to the top of a high-altitude observatory, maybe Mauna Kea in Hawaii or Cerro Paranal in Chile. You carry with you an optical atomic clock in a reinforced case, gently humming. When you compare your mountaintop clock to its sea-level sibling, you'll find it's ticking ever so slightly faster. Gravity is weaker up here, time is looser. You've outrun your basement-dwelling clone by a handful of nanoseconds. Feels good, doesn't it? Now take that same clock into orbit, place it aboard a satellite. Suddenly you're combining gravitational and velocity-based time dilation, exactly what GPS satellites deal with every day. Their atomic clocks tick faster due to altitude and slower due to motion. It's a delicate dance, but the precision is maintained with constant corrections from Earth-based control centers. You're probably thinking, what's the point? Why obsess over time so precise that it doesn't even affect your day? Because precision timekeeping is the backbone of modern technology. Without atomic clocks, GPS would fail, communications networks would desync, banking systems couldn't timestamp transactions, stock markets would collapse into chaos. Deep space navigation? Forget it. In short, the global infrastructure you take for granted runs on relativity. Every satellite, every phone ping, every "you are here" blue dot on your screen. It's all made possible by clocks that know just how much gravity and speed mess with time. And scientists aren't done. They're building the next generation of clocks that can tick in attoseconds. That's a billionth of a second, using trapped ions and quantum entanglement to push precision beyond the limits of imagination. Some even theorize that one day we could use hyper-precise atomic clocks to map dark matter, detecting subtle disturbances in time where invisible mass bends space-time ever so slightly. Imagine that. A clock so sensitive it could feel dark matter walk past it. All because time isn't steady, it's contextual, it's distorted by every motion, every mountain, every ounce of mass. And these clocks, they're the instruments that let us hear it. So here you are, standing in the lab, surrounded by ticking atoms and coffee-stained notebooks. The scientists are giddy but focused. The machines chirp softly with the sound of measured perfection. You lean in and watch a screen flash the tiniest blip. A tick of time, captured, recorded, and compared. A nanosecond lost, a fraction gained. It might not seem like much, but to these clocks, and the physicists who worship them, it's a whole different universe. You've booked the ultimate vacation, not a beach, not a cabin in the woods, not even Mars. No, you've decided to take the most ambitious trip imaginable, one that won't just change your location, but the century you belong to. Congratulations, you're officially in the business of time tourism. Tonight, you're boarding a ship, not one powered by fuel and flame, but by relativity itself. And as it accelerates into deep space, you're leaving behind more than your home planet. You're leaving behind the calendar. Let's play out the itinerary. You and your crew hop aboard a high-speed interstellar vessel. Let's say it's capable of reaching 99.9999% the speed of light, a velocity that, for now, is purely hypothetical but not forbidden by physics. Your mission? A loop around the galaxy, maybe 10 years of travel from your point of view, just a long-haul trip through the stars. You'll play cards, journal your existential crisis, maybe grow a hydroponic tomato or two, and when you return, Earth has aged tens of thousands of years. Your planet has moved on, cities are gone, oceans have shifted, civilizations have risen and fallen, languages have mutated. The top trending song has been playing on loop for 400 years, and it's still stuck in someone's head. You step off your ship, and you are a celebrity from the distant past. Welcome home. This is the time tourism paradox. You've only experienced a decade, but you've skipped entire eras, not by going backward, not by breaking any rules, just by going fast. Let's be clear, this is real physics. The math checks out. It's the same time dilation we've discussed before, just turned up to absurd levels. A traveller moving at relativistic speeds experiences time more slowly than those at rest. So when they return, their internal clock is years behind the world they left. Quirky side note. This idea inspired one of the earliest true relativity-based sci-fi stories. The New Accelerator by H.G. Wells, written in 1901, and later, The Forever War by Joe Haldeman used time dilation to show how soldiers could return home after space battles, to find society unrecognizable. And of course, the Planet of the Apes twist. That's classic time tourism. Leave for space. Return to a planet that's aged without you. You don't need to visit the past to feel like a time traveler. Just take a fast enough detour through the future. Let's scale it down. Even at more modest speeds, say aboard a spacecraft traveling at 90% of light speed, you could reach a star system 100 light years away in just over 40 years ship time. You'd return home after 80 Earth years. You're still in your 60s. Earth is nearly a century older. You've missed your own era, your own culture, probably your favourite TV shows, and the future might not be what you hoped. That's the secret sting of time tourism. It's thrilling, yes, awe-inspiring, but also alienating. The people you knew, gone, the world you understood, obsolete. You're a guest in your own future. And yet, imagine the stories. Imagine standing in front of a crowd of 25th century students trying to explain what coffee shops were, or how everyone used to say LOL out loud for some reason, or how your world debated pineapple on pizza like it was the great moral question of the age. You become a living artifact, a relic with opinions, a human museum piece. Of course, there are debates among physicists and philosophers about whether this kind of time travel is real. Some argue that it's just moving through time slowly, not jumping ahead. But functionally, you've skipped history. You've exited one moment and arrived in another, aged less than everyone else. That sounds like time travel to me. Let's flip the scenario. What if Earth itself sent out time tourists? Imagine a future where interstellar cruises are marketed not just for their destinations, but for the eras they return to. Spend 1 year aboard the Stellar Wanderer, return to Earth in the year 5000. You leave with 50 passengers, you come back with 50 slightly wrinkled passengers and no clue what's happened to the planet. Maybe Earth is a utopia now, or maybe everyone lives inside a sentient cloud and has forgotten how to chew food. Either way, you've bought a one-way ticket to cultural whiplash. This concept also raises deep questions. What happens to your sense of identity if the world forgets you? What does it mean to grow old in a world that's always younger than you chronologically but older culturally? And perhaps most unsettling, what if no one is there to meet you? Time tourism isn't without risk. You might survive the trip, but can you survive the return? Historians still argue whether this idea of skipping forward via relativistic travel should be called travel at all. After all, you didn't navigate time, you just moved slowly through it. But the result is the same. You arrive in the future unchanged. And Earth? Earth has turned the page. Now imagine a future where this is common, where ships leave Earth every decade, each with crews willing to trade their present for someone else's future. Explorers, refugees, romantics chasing the next age. Each return becomes a ceremony, a welcome, a debriefing, and maybe, just maybe, a party. Welcome back. It's been 300 years. Do you still drink coffee? Or maybe it's quieter than that. You land, the world is empty, and you walk, alone, through ruins of glass and stone, the last heartbeat of an ancient species. A relic echoing, a tourist who took one step too far. But let's not end on a sad note. After all, time tourism is built on hope. The hope that the future will still care who you are, that the journey will be worth it, that something incredible is waiting beyond the stars and beyond the seconds. So whether you're dreaming of your next vacation or just standing in line at a coffee shop, take a moment. Think about what it would be like to return one day and find the world forever changed. Not because you left it behind, but because you got here a little too late. You're in a dusty old study now. Wooden shelves sag under the weight of forgotten books. The fireplace crackles. There's a storm outside, classic philosophy weather, and seated around a large oak table, a strange group. On the left, physicists, sharp suits, furrowed brows, equations dancing in their notebooks. On the right, philosophers, wool coats, slower nods, questions scribbled in margins. They're drinking tea, maybe whiskey, but they're all arguing about one thing. Does time actually exist? Tonight, you're not just chasing time dilation, you're chasing time itself, what it is, whether it is, and whether everything you've learned about seconds, clocks, and motion is just a particularly persistent human illusion. Grab a seat. This might get metaphysical. Let's start with a basic observation. You experience time, every second. You remember the past, anticipate the future, and feel the now slipping away constantly like a faulty Wi-Fi signal. But from a physics standpoint, the concept of now is weird. In fact, relativity completely destroys the idea of a universal present. Two observers, moving at different speeds or sitting in different gravitational fields, won't agree on what's happening right now. What's present for you might be past or future for someone else. So where does that leave us? Physicists tend to adopt the block universe view. In this model, time is like space, fully laid out. Past, present, and future all exist simultaneously, like pages in a book. You, the reader, are just flipping through them one at a time, but the book itself is complete. Your birth, your greatest achievement, that time you spilled soup in public, they all still exist in the block. Time doesn't flow, It just is. Your sense of movement through it, that's your brain doing a little illusion magic. This view is called eternalism, and it's a direct consequence of how special relativity mixes space and time into a single entity. Space-time. Quirky side note, Einstein once wrote a letter to the widow of a dear friend, comforting her by saying, "For us believing physicists, the distinction between past, present and future is only a stubbornly persistent illusion." Charming, and also kind of a bummer, but not everyone agrees with this view. Enter the presentists, philosophers who argue that only the present is real. The past is gone. The future doesn't exist yet. Time does flow, and it flows like a river we're all floating down whether we like it or not. They point to our lived experience, memory, change, motion, emotions, the feeling of time slipping forward. Surely that means something. To them, the block universe seems like cold determinism. If the future already exists, do we really have choice? Are we just passengers in a cosmic slideshow? This is where the physicists sigh, because for them, time isn't a feeling, it's a coordinate, like height or width. Need to measure how long light takes to reach a mirror? Cool, time's there for that. Need to feel wistful about your childhood? That's above their pay grade. But even in physics, things get weird. Quantum mechanics, for instance, doesn't always play nice with time. While general relativity treats time as smooth and continuous, quantum theory suggests that everything else, the energy, the particles, the fields, is quantized. So what about time? Could time be discrete, like frames in a film? Some theories suggest yes, that there's a smallest possible unit of time, sometimes called the Planck time, equal to about 5.39 times 10 to the negative 44th seconds. Below that, the concept of before and after might lose all meaning. Historians still argue whether any of this should count as real physics, or if it's just the cosmic version of a bar debate. But more and more scientists are starting to accept that time may not be fundamental. That is, it might not be built into the universe from the start. Instead, it might emerge from something deeper. Some physicists working in loop quantum gravity or emergent spacetime theories propose that time arises from entanglement, the quantum connections between particles. That time isn't a river, but a side effect of how particles are arranged. In this view, you could have a universe with no time at all, just a weird soup of quantum states, and still build clocks and calendars out of correlations. Now that's a hard concept to sleep on. So where does that leave you? Sitting at the table, halfway between two groups who are both trying to make sense of something that slips through fingers like water. The philosophers say time is real but slippery. The physicists say time is relative but measurable. And you've travelled through time just by existing. Let's get more poetic. If time is real, then you're a flame briefly burning in a long dark corridor, visible, momentary, but part of something grander. If time isn't real, then you're a pattern in the void, a memory without a moment, a vibration in a system that doesn't know it's vibrating. Either way, your journey through time is deeply personal, because even if the laws of physics erase the now, your experience of it is rich, meaningful, emotional. Your memories stack, your choices matter, your coffee gets cold if you leave it too long, and that's enough for most of us. Still, if you ever find yourself wondering whether time really exists, just remember, clocks tick, stars age, GPS satellites need relativistic corrections. Your phone calendar definitely thinks time is real, even if it sends you reminders for things you forgot you scheduled at 2 a.m. Time may be a stubborn illusion, but it's a very useful one, and maybe that's the point. You sip your tea, listen to the storm outside, and watch the seconds flicker on a nearby clock. They feel real. That counts for something. You're on the couch now, bathed in the blue glow of a screen, popcorn bowl half full, remote in one hand, time dilation in the other. Because tonight's double feature, time travel in pop culture, where physics meets plot twists and relativity trades its equations for movie magic. And here's the twist. While most of these stories bend science beyond recognition, some of them get surprisingly close. So buckle up. Tonight the laws of motion come with a soundtrack. Let's start with the classics. You press play on Interstellar. The screen opens with dust storms and Dylan Thomas poetry. Then the ship launches, the black hole looms, and suddenly we're on Miller's planet where 1 hour equals 7 Earth years. Sound familiar? That's not just drama. That's gravitational time dilation, dialed up to terrifying beauty. The planet orbits close to a supermassive black hole, and the immense gravity slows time relative to elsewhere. When the crew returns to the ship, their companion, left waiting in orbit, has aged decades. This isn't just accurate, it's elegant. Physicist Kip Thorne, who consulted on the film, ensured that the time effects were based on real equations. Historians still argue whether that's the most scientifically grounded time travel scene ever filmed. Spoiler, it probably is. And yet, even Interstellar has to blur the lines when the plot calls for it. The whole fifth-dimensional beings communicating through gravity and bookshelf Morse code part? Let's just say that part's more emotional relativity, still we love it. Next, you switch to Back to the Future. Marty McFly, hoverboards, DeLoreans that hit 88 miles per hour and suddenly disappear into a streak of light. Fun fact, the number 88 has no scientific basis, it just sounds fast. But the movie does play with a version of time travel that violates relativity. Backwards time jumps. In physics, we don't have any evidence that you can reverse time like that. General relativity allows for closed time-like curves under certain, very exotic conditions, but there's no practical way to implement them yet. Still, Back to the Future gave us iconic paradoxes. What happens if you stop your parents from meeting? Can you erase yourself from existence? Would your photo fade like an Instagram filter malfunction? These are the very questions that physicists and philosophers still love to argue about. Paradoxes of causality that explode when you start treating time like a rubber band. Quirky side note, the original time machine in Back to the Future was going to be a refrigerator, but the filmmakers worried that kids would start locking themselves inside fridges, so they made it a car. Physics dodged a whole new branch of household appliance law. Now, let's enter darker territory, Arrival. A film where time isn't a line, but a circle. Through alien language and non-linear perception, the protagonist begins to remember the future. This plays with the eternalist model of time, that past, present and future all exist equally. That memory isn't tied to sequence but to structure. It's not how relativity describes time precisely, but it captures the feeling of relativity's disorientation, that what's real isn't always what's now. Meanwhile, shows like Doctor Who and Star Trek toss physics out the airlock in favour of pure narrative freedom. In one episode, time can be rewritten with a device that looks suspiciously like a car key fob. In another, paradoxes are treated like minor hiccups instead of universe-destroying threats. Do we care? Not really. We're here for the vibes, but occasionally sci-fi nails it. In The Forever War, Joe Haldeman's novel, soldiers experience time dilation during space combat and return to find Earth culturally alien. That's pure special relativity, emotionally weaponized. Haldeman, a physicist and Vietnam veteran, knew exactly what he was doing. Then there's Planet of the Apes, the original. Astronauts travel at relativistic speeds, land on what they think is a new world, only to discover it's Earth centuries in the future. The time dilation, subtle but accurate. Even Marvel got in on the action. Endgame name drops quantum tunneling and time vortexes like they're on sale at Costco. The actual science, sketchy. But the idea of entering a different frame of reference to shift your position in time, that's relativity adjacent. And yet, all of these stories share one thing in common, a deep, instinctive curiosity about time. Why? Because even when it's twisted beyond recognition, time travel lets us explore the human condition. We want to undo mistakes, see loved ones again, jump ahead, fix things, cheat death, understand loss. We want control over time because we know we'll never really have it. In pop culture, time is a sandbox, but in physics, it's a carefully regulated ecosystem. There are rules, and bending those rules, even just a little, opens doors to stories we can't resist, even if they get the math wrong, especially when they get the math wrong. So as you flip through your favourite time-themed media, books, shows, TikToks about multiverse variants of your dog, remember that these stories are tapping into a deeper truth. That time is weird, and that weirdness is so powerful, it spills into every corner of human imagination. Would you go back and warn your younger self? Jump ahead to see how things turn out? Stay frozen while the world moves on? These aren't just tropes, they're questions. Pop culture is our time lab, a place to test out possibilities without consequences, to imagine time not as a straight line but as a puzzle, a playground, a problem. Historians still argue whether science fiction helps or hurts public understanding of real physics. But one thing's certain, it keeps the questions alive, and questions are where all discoveries begin. So hit pause, think about that. You may not have a DeLorean or a black hole in your basement, but every story you love about time, every twisted timeline, every paradox, every loop is another little spark of curiosity. And curiosity, that's how we keep time moving forward. You're staring at a map of the Earth. It's beautiful blue, rotating gently beneath your fingertips. But now, imagine laying a second map on top, not of continents or borders, but of time. Because tonight you're not thinking about where you are, you're thinking about when you are. And the answer, it depends on where you stand. Welcome to the very real, very quiet truth hiding in our daily lives. The future is already older. In other words, time on Earth doesn't tick the same everywhere. It's close, very close, but not identical. And now that you know how time dilation works, thanks to motion and gravity, you can probably guess why. Let's start with the simplest cause, altitude. Yes, once again, people who live at higher elevations experience time a bit faster than those at sea level. Not metaphorically, not poetically, literally. A person living in La Paz, Bolivia, about 3,600 meters above sea level, will age faster than someone in Amsterdam, only by nanoseconds per year, but still faster. And satellites, they live even farther ahead. The atomic clocks aboard GPS satellites tick faster by 38 microseconds per day, which engineers must constantly correct for. Otherwise, you'd be navigating your way into a wall. But here's where it gets weird. It's not just height. Earth's shape also contributes. Our planet isn't a perfect sphere. It's an oblate spheroid, slightly squished at the poles and puffed out at the equator. That means gravity isn't uniform, and where gravity is weaker, time moves faster. So technically, people near the equator experience slightly slower time than those at higher latitudes. Combine that with differences in altitude, and you get a beautifully messy map of time drift. The result? Even if everyone on Earth synchronized their clocks at midnight one day and then did nothing, no movement, no altitude changes, after a year, those clocks would be off. Not enough to notice, but enough to measure. Tiny ticks of divergence. A planet spinning through a lumpy, imperfect fabric of space-time. And it gets better. Add in motion, say, the fact that Earth rotates at about 1,000 miles per hour at the equator and less at the poles, and you get velocity-based time dilation too. So yes, if you live at sea level on the equator, you're aging more slowly than someone who lives at a high elevation near the poles. Congratulations to all you Arctic mountaineers, you're lapping the rest of us. Quirky detail. Physicists use something called coordinate time to deal with this issue. It's an abstract imaginary universal clock that lets scientists sync up all these slightly off-kilter time zones, not by geography, but by gravitational potential and motion. It's like time zones for Einstein fans. But in practical terms, we mostly ignore these differences, because the effects are tiny, except when they're not. In ultra-precise technology, like financial transactions, quantum networks, and deep space communications, these shifts in time start to matter. A lot. Timing errors, even on the order of nanoseconds, can cause massive headaches in global systems. So we adjust, we correct, we compensate, we respect time, not just as a clock but as a landscape. And that's where things get philosophical, because if two people on Earth can disagree about how fast time is passing, what about people across galaxies? That's right. Let's zoom out. Imagine someone on a planet orbiting a neutron star, a hyper-dense remnant of a collapsed star where gravity is immense. Their time moves painfully slow compared to someone floating in intergalactic space, where gravity is almost non-existent. From one perspective, the universe is crawling. From another, it's sprinting. So when we ask questions like, what's happening right now in another galaxy? Relativity quietly leans in and says, that question doesn't make sense. Because now is a local illusion. In fact, two observers moving relative to one another will disagree on the simultaneity of events. One may say, these things happened at the same time. Another may say, no, one happened first, and both are correct. There is no universal clock, no central beat, just a messy web of ticking, each node dancing to its own rhythm. This is called the relativity of simultaneity, and it makes simple questions impossibly complex. When exactly did that star explode? What is the present moment on Mars right now? Are we all living in the same second? The answer is, sort of, from a certain point of view, but not exactly. Historians still argue whether our obsession with now is biological or cultural. Some say it evolved because living organisms need to respond to immediate threats. Others argue it's just how consciousness feels from the inside. But physics doesn't care how it feels. Physics says time is local, a thing you carry with you like a sleeping bag or a favourite playlist. And across the universe, countless civilizations, if they exist, might be living out their nows, all slightly askew from each other. No one truly aligned, a slow cosmic drift of seconds and epochs. That makes communication difficult. If we send a message to an alien species 1,000 light years away, they receive it 1,000 years in the future. If they reply instantly, we hear them 1,000 years later. The conversation takes 2 millennia. We could be long gone, our cities, dust, our oceans, steam. But the message arrives anyway. This is the tragedy and the poetry of time dilation. The faster you go, the slower you age. The higher you live, the faster time moves. And the farther you look, the older everything becomes. Because light, that loyal messenger of reality, always arrives late. Even the stars you see right now, most of them aren't there anymore. They're echoes, ancient photons still making their way to you, long after their source has died or moved on. You're living in a patchwork of pasts stitched together by light's stubborn slowness. And yet, this delay is a gift. Because without it, we'd have no window into the universe's history. No chance to see galaxies being born. No glimpse of the cosmic microwave background. The afterglow of the Big Bang still reaching us after 13.8 billion years. Time delays are not a flaw. They're the only reason we can observe anything at all. So as you sit on your side of the Earth, in your time zone, on your elevation, moving through your personalized sliver of time, remember, you're not in sync with the rest of the universe. You never were. And that's okay, because the future is already older somewhere, and you're catching up second by second, heartbeat by heartbeat, ride by relativistic ride. You're back where it started, not in your bed, not in a spaceship, not at the edge of a black hole, but somewhere quieter, somewhere smaller. You're standing on the sidewalk, maybe outside your house, maybe next to a lamppost. It's night, and the stars above are still doing their ancient, unhurried dance. The air is still, your feet are warm in your shoes, and you're holding a watch, not a fancy one, not an atomic clock or some experimental laser lattice timepiece, just a watch, one that ticks, one that keeps you anchored. But now you know what it isn't doing. It's not ticking at the same rate as all the other watches in the world, or in orbit, or next door. It's doing its best, but it's wrong, in a way that's delightfully, definitively relativistic. Because tonight you've lived it all. You've fallen into gravity wells, floated beside satellites, flirted with the speed of light, slept through centuries, crossed philosophical battlefields, watched particles outrun their own lifespans. You've even stood at the mouth of a wormhole and wondered whether you had the courage to step through. And now you've come full circle to one final realization. Time travel is real. It doesn't look the way movies sell it. There's no blue flash, no spinning dials, no whooshing, but it's real. Because your experience of time, how fast or slow it moves, how long your seconds last, changes depending on where you are and how you move. Every person on Earth is already a time traveller slipping forward on a slightly different schedule, and while we can't go backward, not yet, we can move forward at different rates, with speed, with gravity, with altitude. The universe doesn't stop us, it simply adjusts. Let's walk through what that means. Imagine 2 astronauts side by side on Earth. They're twins, because of course they are, and they agree to part ways. One boards a ship and travels near light speed for 20 years. The other stays on Earth, grows old and eventually welcomes their younger sibling home. The one who travelled? Barely aged. That's not theory. That's the twin paradox, verified in tiny increments by real science. On planes, in labs, in GPS satellites. We have time travellers among us. We just call them astronauts. The same logic holds for elevation. Clocks on mountaintops run faster than clocks at sea level. Your head is aging faster than your feet. Walk up the stairs. You've leapt forward, fractionally. And it's not just humans and clocks. Muons, those little cosmic messengers, live longer than they should simply because they're moving so fast. Time bends around them, giving them just enough life to reach the ground and leave their mark. It's beautiful, it's weird, it's real. Quirky final tidbit. If you had 2 atomic clocks and stood one atop the other, just a few inches apart, they would tick differently. That's how sensitive we are to time's malleability. You don't need to orbit a star or crash into a singularity or just stand up. Of course, most of this goes unnoticed in daily life. Our hearts still beat, coffee still cools, meetings still run too long. But now you know what's happening under the hood. Now you know the truth your watch won't tell you. That time is personal, local, flexible. Historians still argue whether time dilation should really be called travel. But ask any astronaut, any physicist, or any well-informed watchmaker, and they'll tell you, we've already arrived. Every time you move, you travel differently through time. Every second you experience is yours alone. And when you start layering that across a planet, a solar system, a galaxy, across all the observers and all their frames of reference, you begin to see the real shape of time. Not a straight line, not a river, but a web. A shimmering, vibrating, constantly shifting network of clocks and moments and perspectives, where what's now depends on who's asking, where what's next is always relative, and where home might just be the place where your clock ticks the way you remember. So now, you glance at your watch one more time. It's still ticking, but you know better now. You know it's lying to you, lovingly, softly, just a little, because you've been somewhere it can't follow. You've stepped outside its rules, and you're coming back changed, not in age, not in years, but in understanding. You're a time traveller, you always have been, and now as the last echoes of space-time slip into silence, let yourself drift. Loosen your grip on the ticking, the counting, the measuring. You don't need to follow the seconds anymore. They've served their purpose. Your body, tired but curious, begins to settle. The math fades, the theories soften. You return to your own quiet corner of the universe, a place where clocks are just background noise and time, for once, is gentle. The stars above still burn, but you don't need to reach them tonight. You've already gone further than light speed. You've already slowed time with your breath, with your thoughts. Now, it's enough to be here, wherever here is on your personal timeline. Let the concept of time, of future and past, of fast and slow, become blurry. Let it fade into something simple and forgiving, a warmth, a stillness. A moment suspended not because time has stopped, but because you have. Just for a while. And tomorrow, when your feet touch the ground again, and the clocks resume their polite lying, carry this with you. Time isn't fixed, but neither are you. You move with it, shape it, bend it. And every step you take is another ripple in the fabric of the universe, another journey through time. So rest now, traveller, you've earned it.